When you turn on a light switch, the room brightens so quickly it feels instant. But light doesn't move infinitely fast. It crosses the room in about 20 nanoseconds. You'd never notice. Even across a football field, light arrives in under a microsecond. The delay is invisible to us. We live in a world where light seems immediate, where the fabric of reality responds so quickly that we never question it. If you enjoy these deep dives, you can subscribe. It helps more than you think. So, let's begin. There's a number written into the structure of everything. It appears in equations about gravity, about electricity, about how particles behave when they move fast. It shows up when we talk about black holes, about the edge of the observable universe, about why atomic clocks on satellites tick differently than clocks on the ground. That number is the speed of light. We call it c. It's approximately 299,792 kilometers per second. And it's not just the speed at which light happens to travel. It's something more fundamental than that. The speed of light is woven into the geometry of space-time itself. It's the rate at which cause and effect can propagate. It's the conversion factor between space and time in Einstein's equations. When we write down the mathematics of how gravity warps space-time, c appears there. When we describe how electric and magnetic fields interact, c emerges naturally from those relationships. It's not a property of light. Light simply moves at the universe's maximum speed because photons have no mass. Anything without mass travels at c. Anything with mass cannot. This speed limit isn't arbitrary. It comes from two properties of empty space. In the 1800s, James Clerk Maxwell unified electricity and magnetism into a single theory. His equations described how electric fields create magnetic fields, and magnetic fields create electric fields, in a kind of mutual propagation. When Maxwell worked through the mathematics, he found that electromagnetic waves should travel at a specific speed, determined by two constants. One is called the permittivity of free space. It measures how much empty space resists an electric field. The other is the permeability of free space. It measures how much empty space allows a magnetic field to form. If you take the permittivity, multiply it by the permeability, take the square root of that product, and invert it, you get the speed of light. Maxwell realized he'd stumbled onto something profound. Light was an electromagnetic wave, and its speed was fixed by the properties of the vacuum itself. This had strange implications. If the speed of light depends only on properties of space, then it shouldn't matter how fast you're moving when you measure it. You might expect that if you chase after a beam of light, it would appear slower to you, but experiments showed otherwise. Light always moved at the same speed relative to any observer, no matter their motion. This fact disturbed physicists for decades. It seemed to violate common sense. How could something move at the same speed whether you were standing still or racing toward it? Einstein resolved this in 1905. He proposed that space and time aren't separate, fixed backgrounds. They're flexible. They adjust themselves so that the speed of light remains constant for everyone. If you start moving very fast, time slows down for you. Distances contract along your direction of motion. These aren't optical illusions. They're real changes in the structure of space-time, and they happen in exactly the right amounts to keep light moving at c in all reference frames. This is special relativity. The speed of light isn't just a speed. It's the pivot around which space and time trade off against each other. When you move faster, approaching a significant fraction of the speed of light, time dilation becomes noticeable. If you're on a spaceship traveling at 90% of c, every second that passes for you corresponds to about 2¼ seconds passing on Earth. Your clocks run slower. Your biological processes run slower. From Earth's perspective, you age more slowly. This isn't because of anything happening to your body specifically. It's because time itself flows differently for you, and the factor by which time dilates depends on how close your speed is to c. The closer you get, the more extreme the effect. Similarly, your mass seems to increase, or rather, the energy required to accelerate you further grows without bound as you approach c. At everyday speeds, accelerating something requires a predictable amount of energy. double the speed, quadruple the kinetic energy. But as you get closer to the speed of light, the relationship breaks down. At 99% of c, you need about 7 times more energy than you'd expect classically. At 99.9%, it's more than 20 times. The closer you get to c, the more energy you need, and the requirement escalates toward infinity. You can never actually reach c if you have mass. There isn't enough energy in the universe to get you there. This limit shapes everything. It constrains how fast information can travel. It determines the size of the region of space we can ever observe or influence. It sets boundaries on computation, on communication, on causality itself. When something happens over here, the universe over there doesn't know about it instantly. The news propagates outward at the speed of light. For an event happening right now on the other side of the galaxy, we won't see it for tens of thousands of years. Cause and effect respect this limit. You cannot send a signal, move an object, or exert an influence faster than c. Now imagine c were different, not by a small amount, 10 times larger. Instead of roughly 300,000 kilometers per second, imagine light traveled at 3 million kilometers per second. What would this mean? The first thing to understand is that this wouldn't just change how fast light moves. It would alter the fundamental exchange rate between space and time. The formulas of relativity contain c as a scaling factor, time dilation, length contraction, relativistic mass increase. All of these depend on the ratio of your speed to the speed of light. If c is 10 times higher, then to experience the same relativistic effects, you'd need to move 10 times faster. A spaceship traveling at 90% of our current c would experience strong time dilation, but if c were 10 times higher, that same spaceship, moving at the same absolute speed, would only be moving at 9% of the new c. The relativistic effects would be negligible. You'd need to reach speeds of several million kilometers per second before relativity started to matter noticeably. For most of human experience, for almost everything we do or build, this means the universe would feel more classical. We live in a regime where speeds are tiny compared to c. Even our fastest spacecraft move at speeds that are a minuscule fraction of light speed. Voyager 1, leaving the solar system, travels at about 17 kilometers per second. That's about 0.006% of c. Relativistic effects at these speeds are utterly insignificant. We don't experience time dilation in daily life. We don't notice length contraction. We don't need to account for relativistic momentum when driving a car. If c were 10 times higher, we'd be even further from that threshold. The universe would behave, in practical terms, even more like Newtonian physics predicted. But the change would ripple outward in subtle ways. Consider the structure of space-time itself. General relativity describes gravity not as a force, but as the curvature of space-time, caused by mass and energy. Massive objects bend space-time, and other objects follow the curves, which we perceive as gravitational attraction. The Einstein field equations relate the curvature of space-time to the distribution of mass and energy. And in those equations, the speed of light appears. It sets the scale. It determines how much space-time curvature a given amount of mass produces. If c were larger, space-time would be stiffer, in a sense. The same mass would produce less curvature. Gravity would still exist. Objects would still attract each other, but the strength of gravitational effects relative to a given mass would weaken. The Schwarzschild radius, which defines the boundary of a black hole, is proportional to the mass of the black hole and inversely proportional to c squared. If c increases by a factor of 10, c squared increases by a factor of 100. The Schwarzschild radius for a given mass would shrink by a factor of 100. A black hole with the mass of the Sun currently has a Schwarzschild radius of about 3 kilometers. If c were 10 times higher, it would shrink to 30 meters. Black holes would still form, but they'd be more compact. The event horizon, the point of no return, would be closer to the center. Stars would also change. The processes inside stars depend on the balance between gravity pulling inward and pressure pushing outward. That pressure comes partly from the heat generated by nuclear fusion. Fusion releases energy when light nuclei combine into heavier ones. The rate at which energy escapes from the core depends on radiation. Photons carry energy outward. The behavior of photons, their energy, their momentum, depends on C. If C is higher, photons at a given frequency carry more energy. The relationship between frequency and energy is given by Planck's constant times the frequency. But the momentum of a photon is its energy divided by C. If C is 10 times higher, a photon of a given energy has 10 times less momentum. Radiation pressure, which helps support stars against collapse, depends on photon momentum. With higher C, radiation pressure would be weaker for the same energy flux. This shifts the internal dynamics of stars. They might collapse more easily or burn through their fuel differently. The lifetime of stars, their luminosity, the conditions under which they form, all of this would shift. The universe would still have stars, but they wouldn't be quite the same stars we see. The early universe would be different too. In the first moments after the Big Bang, the universe was extremely hot and dense. Particles moved at speeds close to c. Relativistic physics dominated. Processes like particle creation, annihilation, and scattering all depend on c. The rates at which particles interacted, the energies at which phase transitions occurred, the balance between radiation and matter, these would shift if c were different. The cosmic microwave background, the afterglow of the Big Bang, would have a different temperature distribution. Tiny fluctuations in density, which later seeded the formation of galaxies, depend on how quickly perturbations could propagate in the early universe. That propagation speed is limited by c. A higher c means disturbances spread faster. The pattern of structure formation, the scale of the largest coherent structures, the timeline of cosmic evolution, all of this hinges on the value of c. Inflation, the rapid expansion thought to have occurred in the universe's first fraction of a second, also depends on c. Inflationary models describe space-time expanding faster than light could cross it. That's not a violation of relativity. Space-time itself can expand at any rate, but the distance scale over which quantum fluctuations become classical structures depends on the interplay between the expansion rate and c. If c is higher, the horizon size during inflation is larger. The imprint inflation leaves on the universe would be different. The observable universe today, which is the region from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. That's larger than the age of the universe times c, because space-time has been expanding. If c were 10 times higher, light could travel 10 times farther in the same time. The observable universe would be vastly larger. We'd see galaxies 10 times farther away. We'd see light from epochs 10 times earlier, in a sense. The cosmic horizon, the boundary of what we can ever observe, expands. Gravitational waves, ripples in space-time caused by accelerating masses, also travel at the speed of light. They propagate at c because they're distortions in space-time itself, and c is the speed at which changes in space-time propagate. If c were 10 times higher, gravitational waves would travel 10 times faster. Events like colliding black holes or neutron stars would send ripples across the universe more quickly. The timescale for gravitational wave signals to reach us would shrink. Detecting these waves, measuring their properties, understanding their sources, this would all change because the signals would arrive on different timescales. On a smaller scale, think about atoms. The fine structure constant, a dimensionless number that characterizes the strength of electromagnetic interactions, depends on several fundamental constants, including c. It's approximately 1 over 137. If c changes, the fine structure constant changes. This affects how tightly electrons bind to nuclei, the spacing of atomic energy levels, the way atoms absorb and emit light. The chemistry of matter depends on these details. If c were 10 times higher, the fine structure constant would be 10 times smaller. Electromagnetic interactions would be weaker. Atoms would be slightly larger. Chemical bonds would behave differently. The entire periodic table, the way elements combine, the stability of molecules, this would shift. The universe would still have chemistry, but it wouldn't be the same chemistry. Whether life as we know it could arise in such a universe is unclear. Life depends on intricate chemical processes. Change the rules, even slightly, and you might break the pathways that allow complexity to emerge. For human technology, a tenfold increase in C would have noticeable effects. Consider GPS. The global positioning system relies on precise timing. Satellites orbit Earth, broadcasting signals. A receiver on the ground picks up signals from multiple satellites and calculates its position based on the time delays. These delays are tiny. Light takes about 67 milliseconds to travel from a satellite in medium Earth orbit to the ground. That's already fast, but the system needs to account for relativistic effects. The satellites are moving and are in a weaker gravitational field than the surface. Time runs slightly faster on the satellites due to the weaker gravity, and slightly slower due to their motion. The net effect is that satellite clocks run about 38 microseconds per day, faster than ground clocks. If C were 10 times higher, these relativistic corrections would be 100 times smaller. The system would still need precise timing, but the corrections for relativity would be negligible. GPS would work essentially the same, just with less concern for relativistic effects. Communication across distances would change. Right now, there's a delay when sending signals across space. Light takes about 1.3 seconds to reach the moon. It takes about 8 minutes to reach the sun. Conversations with astronauts on the moon have noticeable lag. Commands sent to Mars rovers take between 3 and 22 minutes to arrive, depending on where Earth and Mars are in their orbits. If C were 10 times higher, these delays would shrink by a factor of 10. Talking to someone on the moon would have a delay of about 1/10 of a second, barely noticeable. Mars communication would take between 18 seconds and 2 minutes. Interplanetary operations would feel more immediate. Deep space missions would be easier to manage in real time. Astronomy would change profoundly. We observe distant objects by collecting the light they emit. The farther away something is, the longer its light takes to reach us. When we look at a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. The universe has a history written in light. If C were 10 times higher, light from that same galaxy would reach us in 1/10 the time. But this doesn't mean we'd see more distant objects. The age of the universe is about 13.8 billion years. If C were 10 times higher, light could travel 10 times farther in that time. The most distant objects we could observe would be about 10 times farther away, measured in distance. But because space-time expansion matters, the relationship is more complex. Still, the overall effect is that our window into the universe would expand. We'd see more of cosmic history. Events that are currently beyond our observational horizon would become visible. Particle physics would shift, too. High-energy physics experiments accelerate particles to speeds very close to C. The Large Hadron Collider, for instance, accelerates protons to 99.99999% of the speed of light. At these speeds, relativistic effects dominate. The protons gain enormous energy, and when they collide, that energy can create new particles. The maximum energy achievable in a collider depends on how close you can get to C and how strong your magnetic fields are. If C were 10 times higher, you'd need 10 times more energy to reach the same fraction of C. But the absolute speed at which relativistic effects become important would be much higher. Experiments would probe different regimes. Particles we currently study only at high energies would behave more classically. The thresholds for creating certain particles, the cross-sections for interactions, the way particles decay, all of this depends on C. Even quantum mechanics would feel the change. Quantum field theory, which describes particles as excitations in fields, relies on relativity. The equations of quantum field theory are constructed to respect Lorentz invariance, the principle that the laws of physics look the same in all inertial frames. This invariance is built around C. If C changes, the structure of these theories shifts. The relationship between energy and momentum, the behavior of virtual particles, the vacuum energy, all of these have C embedded in them. Quantum entanglement, the strange correlation between distant particles, doesn't allow faster-than-light communication even in our universe. Increasing c wouldn't change that. Entanglement doesn't transmit information faster than light. It's a correlation, not a signal. But the limits on quantum information processing, the maximum rate at which quantum computers could operate, the speed at which decoherence occurs, these would shift. A higher c means faster limits on certain processes. One thing that wouldn't change, though, is the existence of a speed limit. Even if c were 10 times higher, it would still be a maximum. You still couldn't exceed it. Relativity would still exist. The mathematics wouldn't go away. The Lorentz transformations, the equations that describe how space and time mix, would still apply. They'd just apply at higher absolute speeds. The fundamental structure, time dilation, length contraction, the equivalence of mass and energy, all of this remains. It's scaled differently, but it's still there. Causality would still be protected. You couldn't send information backward in time. You couldn't create paradoxes. The universe would still have a logical, consistent structure. It would just be a universe where the threshold between classical and relativistic behavior is much higher. This raises a deeper question. Why does c have the value it does? Why 300,000 kilometers per second and not something else? We don't know. The speed of light emerges from the permittivity and permeability of free space. But why do those have their particular values? They're measured quantities. We can determine them experimentally, but we don't have a theory that predicts them from deeper principles. This is true for many fundamental constants. The strength of gravity, the mass of the electron, the charge of a proton. We measure these, but we don't know why they are what they are. Some physicists speculate that different regions of a larger multiverse might have different constants. In some places, c might be higher. In others, lower. Perhaps only in regions where the constants fall within certain ranges can complexity, stars, planets, and life emerge. We happen to find ourselves in a region where the constants allow us to exist. This is the anthropic principle. It's not a satisfying answer in some ways. It doesn't explain why our constants have their values. It just says that we observe these values because we couldn't be here to observe anything else if they were too different. But even within this framework, imagining different values helps us understand what the constants do. By thinking through what changes if c is 10 times higher, we see how deeply c is embedded in the fabric of reality. It's not just about light being faster. It's about the relationship between space and time being different. It's about the strength of gravity shifting. It's about the dynamics of stars, the evolution of the universe, the behavior of atoms. Every structure we see, from galaxies to molecules, depends on the balance of fundamental forces and constants. Change one, and the whole edifice shifts. If c were 10 times higher, the universe would still obey the same fundamental laws. Relativity would still govern motion and space-time. Quantum mechanics would still describe the behavior of particles. Gravity would still curve space-time, but the details, the scales, the thresholds, all of this would be different. Stars might burn differently. Black holes would be smaller. The observable universe would be larger. Atoms would be slightly bigger. Chemistry would shift. Life, if it could arise at all, would emerge from different processes, in different forms. We can't know if conscious beings could exist in such a universe. Perhaps they could. Perhaps they'd look up at their sky, measure their version of c, and wonder what would happen if it were different. The constants of nature define the universe we inhabit. They set the rules. They determine what's possible. We live in a universe with a particular speed of light, a particular strength of gravity, particular masses for particles. And those choices, random or not, have consequences. They make galaxies the size they are. They make stars burn for billions of years. They make atoms stable. They allow chemistry. They permit complexity. Changing c doesn't just tweak one variable, it reshapes the entire landscape of what exists and how it behaves. There's a kind of humility in recognizing this. We think of the universe as vast and varied, and it is. But it's also contingent. It could have been otherwise. The laws we observe aren't arbitrary, but their parameters might be. And within those parameters, everything unfolds. The way light crosses a room, arriving in nanoseconds. The way stars hold themselves against collapse. The way time flows differently near a black hole. The way we can look out and see galaxies billions of light years away, their light having traveled for eons to reach us. All of this traces back to the constants, to the numbers written into the equations. Imagining C 10 times higher doesn't give us new physics. It gives us perspective. It shows us what our physics depends on. It reveals the role CE plays, not just as a speed, but as a structural element of reality. And it reminds us that the universe we experience, familiar and predictable as it seems, is built on a foundation of quantities we measure, but don't fully explain. The speed of light in the end is more than light. It's the pace at which reality itself moves, and that pace shapes everything.